Okay, welcome everyone to the ZX seminar. I'd like to introduce Nicolas Heurtel to talk about a complete graphical language for linear optical circuits with finite photon number sources and detectors. Take it away, Nicolas.
Thanks, Alex, and thank you for the invitation and the organization of the seminar. I'm very glad and happy to present that work. So, as Alex said, I will talk about my recent work, which is about optics, so optical circuits, graphical language, with more components. So, in particular, sources and detector. So, before presenting the plan, I will explain a bit the motivation of the work. So, I guess as it is a ZX seminar, you won't be the most difficult public to motivate for the graphical stuff. But I would like to specify maybe one point of motivation. So we know that graphical language is very useful for many things because we have more insight on some things and so more applications. And in particular, it is very well suited to study equivalences between diagrams. Specifically, it also sometimes finds a unique representation of processes, so normal forms sometimes. And so that's kind of the question that we will ask now. So graphical language, there are many. Are there diagrams for optics? So the answer is yes. So there are many, more and more languages that can represent linear optical processes. So there was QPath, so by Giovanni De Felice and Bob Cook. There was Love, that Alexandre Clément, a joint work with Alexandre Clément, Shane Mansfield, Simon Perdry, and Benoît Valiron. There was a recent paper of Octop ZX, which was a continuous variable, so infinity stuff. And also all other works with Booth, Comfort, and Carrette. However, all those works are either not fully photonic, so they are generators which are not directly linear optical components, and or maybe sometimes they are too restrictive. For instance, love, for those who know it, you don't have all the sources, and there is no many photon semantics. And so the purpose of the work and the purpose of the presentation is to go forward toward the question of, is there a unique way to represent linear optical circuits with sources and detectors? The answer of this work is then to propose that form that I will detail later, but just to have a picture right now to spoil everyone, it will look like that. So basically a circuit with in the auxiliary input generic state and some effect, which will be some detectors. And a byproduct of that, as we have like a unique representant of such processes, we can derive a complete equational theory with those generators. So that's the motivation, like to understand how to come up with that and the proofs, and also the reason behind the equations. And so now we can look at the plan of the presentation. So first, it will be a quick reminder of optics, and in particular with the simple semantics, which is a single photon semantics. So we will just deal with linear optical circuits when there is just one photon. It will be easier, and also it will be a good start to then understand the complexity of adding photons. The second step will be to see what happens with photons. So basically to understand how the generators, how the diagrams are basically working with photons. And then we will see the lo-fi calculus, which is like the kind of circuits I show you earlier. And we will try to look at the normal form, so like to try to rewrite into the form I just show you. And the last, maybe the most important part of the talk for you, who are not maybe working with optics, is like the key points of the proof. So basically in the proof, I introduce some operators, some techniques, and hopefully that could be useful for the people who listen to that talk. So I am talking to the ZX seminar, but there is no ZX. However, hopefully the last part, so where we go into the proof, may be useful to do links with ZX or other graphical languages. Also, I didn't precise it, but feel free to ask any question during the talk. So please interrupt me or raise a hand. I'll be glad to answer during the talk. And I think it's better if there is something which is unclear to answer directly. Without further production, let's talk about loop circuits. So loop circuit basically is a prop, or just circuit are generated by those components. So LOP stands for linear optical polarization and preserving polarization, because we don't talking about polarization here. Those circuits, as any other graphical language, can be composed sequentially and also in parallel. And one example of such circuit can be that one. For those components, we can introduce what we call a single photon semantics. So what is that? So when you have your circuits, what are the states? How do we encode the information? So usually we use what we call the spatial encoding. So basically, so it's optics. So imagine you have one photon. You have many wires on your circuits. Then the state is basically representing where the photon is. So you will have ket like that with R0, the photon is not here, and the 1, where the photon is. So important to have that in mind, but for n wires, so then the dimension is n, and the state of space is just c up to n. And so the semantic is quite also natural. You can define it inductively like as follows. In particular, the semantic of the phase shifter is just adding a phase. And the bit splitters, as you can see, either the photon is on the top wire or the bottom, and it will do a superposition of the two. For those more familiar with quantum gates or just Pauli rotations or that, you can see that the beam splitters has also a rotation on the x-axis, just that the angle is different, but you can just interpret the beam splitters as a rotation. And so one question that we can have for just circuits of that is there a unique representant circuit representing that? And so the answer is yes. And so it's kind of looks like that. It's a triangle. So just to specify maybe some things to know. So it's always shaped like that, as a triangle. And it is universal for all unitaries. Also, there are some properties on the angles so that the circuit is unique. So for instance, if you have some zero angle for theta, then all the theta under it and the diagonal are also zero. So there are some conditions for that circuit to be unique, but in general, just imagine a triangular circuit with n square. Oh, sorry. Yes, n square coefficient parameters, basis. And so with that unique normal form, we had a complete equational theory. So it was a joint work with Alexandre Clément, Shane, Simon, and Benoit. And we basically introduced a complete equational theory. So maybe some equations are quite easy to understand, like if you have zero phases, you have the identity. Some other are more a bit complex, not in particular the last one. So you can just see that as some computation of rotation and phases, and you inverse the order of the rotation, and so you have some phases there. And so it was the first complete equational theory for that types of circuits. And in the work of what I did, which is an archive, I just simplify a bit the equations. So I remove all the phases. I proved that it was not necessary to have that phases. We could derive that equation with the others. I added one more phases. So the reason was before you can see that there were three phases on the right and three angles on the right and four angles on the sorry, three on the left and four on the right. And so it was not easily reversible. And so I added the phases, so both have the same power, basically, in universality. And so it's easily reversible, and you have explicit formula this time for both ways. And also with that, we could remove so in the end, we have a simpler equational theory, which is either basic relations like zero phase and zero beam splitters, or just different composition of rotations. So that was for the semantics with one photons, just with beam splitters and phase shifters. What happens when we add more photons? So we have to know that photons can bunch, so physically, that means that can be in the same position. So before we just say, oh, there is one photon there. When there are many photons, they can all be there, or they can be dispersed in all the wires. To represent that, we use what we call Fock state. So basically, it's just a set of integers order, just to mention how many photons we have in each wire. So that the basis, and of course, you can have a superposition of the states for the state. So what happens, for instance, after beam splitters? So in general, if you have one photon on the top and one photon on the bottom, then you have a superposition. You have sometimes the state 2, 0, the state y1, and state 0, 2. In general, if you have K1 and K2, then you will have all the combination which conserve the number of photons. So all the Fock states where the sum L1 plus L2 is conserved. So that's it. However, if we just talk about beam splitters and phase shifters, if we add that semantics with many photons, it is still complete. Like there is a perfect isomorphism between the two. And so basically it's not much more, I mean, it's more complicated with the formula. And then I'll show the formula, but it's a bit more complex. However, we still have the property of uniqueness. And so if we just talk about beam splitters and phase shifters, even with the many photon semantics, it will still be unique and complete. However, when we talk usually about adding photons, we just don't talk about photons entering beam splitters and phase shifters. We talk about auxiliary photons and detectors. So we have to know that in linear optical quantum computing, very, very, very often, circuits are just not beam splitters and phase shifters, but also there are some ancilla, auxiliary states, and some effects, some post-selection, some detection. So graphically, it would mean like that. For instance, that type of circuit, so we can maybe understand a bit what it is. We have two free wires in the input, free wires on the output, and we fix here that we sent one photon on the last two wires on the input. And what we have at the end, we post-select on detecting one photon on that wire and one photon here. If we do that selection, then that circuit is implemented as CZ, for instance. So I just show the logical operation on the right. So that's very common in optics to use that to perform logical operations or to do many other things. So when we mean adding photons, we mean adding sources and detectors and post-selection schemes. And so what happens if we just add, for instance, sources with only ones or zero? So the most basic sources and ancilla we can have. So let's just imagine, for instance, an optical circuit, so M. So M is like the unitary behind the semantics of the circuit composed of phase shifters and beam splitters. And we add once on the input and once on the output. What happens? That it is a scalar, so the amplitude, we see there is no input, no output. And for those who know it, it's the permanence of the matrix M. The permanence is basically the sum in the matrix of all the permutations So it's the same as a determinant, but without the signature of minus. And that permanent is very hard to compute. And so if M, for instance, is a unitary or a real matrix, it will be. So, okay, why not? My point is that you can have a very easy, very simple circuit, which is also the same scalar. So that circuit, for instance, if M is real, is also having the same scalar. And so there is a question about, can we write one into the other? That's what we would like to do. Like we add photon, we add sources, we need that. How can we write it? That simple example is just not to justify the following, but at least to give some insight about how hard it is to rewrite optical circuits. There are also Sharpie hardness results in ZX for many things. But I'm just saying that with a simple example, there is a complexity in just writing those two diagrams. How to deal with that? So for instance, QPath, so from Giovanni, the Phillips and Bob Cook, they use superposition of diagrams. To simplify that big diagrams or the one, they just say, oh, we just rewrite all the permutation with all the diagrams. And so they solve that difficulty with that. My proposition in my work was not to do that, but to introduce generic components. We can't just rewrite those two circuits with just sources of one, or at least it seems very difficult. So one way to do it is like to allow very generic sources and very generic detectors. What I mean by that is like F here can be any superposition of a Fock states. Okay. So now I say, okay, I introduce very generic states. It seems a bit like cheating. Like, okay, I can do any state at the input. I can do any detection at the output. I will try to explain it's not so bad. So basically, if the state is normalized, it has a physical meaning. Like any state which is normalized in a source is a state that we can have physically. It's not absurd. So up to normalization, every source and detector here have a physical sense. Also, some states, even though it's just one photon or two photons, like superposition of 0 and 1, for instance, in one mode, can be directly created. So there are some sources that can create states which are just not one photon. So there is like an interest also to be able to model that. So it's not completely absurd to have some superposition directly inside the sources. And also, to go further, optics is very modular. So basically, we use like some part of circuits just to create one state. And so it will be also very convenient to say, oh, I want to create a Bell state, for instance, Phi plus. I just want to represent my source with a Bell state. In practice, it will be like the big circuit on the right, but I'm happy with doing that. So yes. So the point of that, before going to the semantics and syntax and semantics, was just to say there is a big complexity in adding just sources and detectors, even if it's just 1 and 0. There are circuits that seem very hard to rewrite into and to find rules to do that. And so the proposition of the work is to introduce generic states in the sources and detectors. So yes, Simon?
I was just wondering why you specified some of the angles, but not all of them. So theta 1, theta 2. So is there any reason for this?
So yes, because the theta is not just a multiple of pi. It's just like not a nice expression. So I just
Okay.
I don't have the numerical value, but it is in the paper though, I think, or in the, but yes.
Okay, thank you.
But it is a fixed value. It's not a variable. It is a fixed theta. Okay. So now, yes, just before I said generics first, but as the title said, I'm only working with finite superposition Fock states in the sources and detectors. So why finite? It's not because things wouldn't be defined. In particular, like it would be very well defined on the infinity Hilbert space of Fock space. However, it's just because I couldn't prove it. I couldn't prove the uniqueness by even though the sources and detectors, if they were infinite, then I don't the proof that I will explain to you doesn't work anymore. So it's more about a technical restriction more than a theoretical one. Okay, so the Lo-Fi calculus. So basically, generated, again, it's a prop generated by those components. So this time there are two more components, sources and detectors, that can parameterize by vectors. And again, like last time, they can be composed sequentially or in parallel. The semantics now. So we also define the semantics inductively. So of course, like the swap, if there is K1, K2, you just swap. So for those types of operators, it's okay. For the source and detectors, basically, as we directly write or we parameterize the source by the vector itself, then the semantics is basically the vector. Just to mention, I didn't go into the details, or I didn't write the space precisely of F and G, but the G is a bra, which would be a set, a sum of bra, and F will be a sum of kits. The phase, when there are many photons, like the K photons at the input, there will be a K times phi phase at the output. And of course, the most complicated components is the beam splitters. When there are K1 and K2 photons, they're basically like, so the number of photons is preserved. So you still have a sum over L1 plus L2 equals to K1 plus K2. But the coefficients behind that is kind of combinatory. It's just basically imagine just photons bunching. Like there is some kind of binomial intuition, but in the end, it's not that easy to represent. But we don't choose the semantics. It's like the physics who is like that. So we will work with that semantics from now on. Just to mention, like just to compare, for before, like when there was one photon and n wires, it was just the number of wires, the dimension. Here, the number of states is far more. So just to explain again, like how big the space is. And so now the question that we will try to answer now is like, is there a unique representation of low-fi circuits? So before, when there was like just bit splitters, we know, for instance, that if there is a different angle, it is different. But it's not so clear if you allow auxiliary states and auxiliary detections. Maybe there is an input state and also an auxiliary detection that's allowed to have the same process. It's even less clear when the circuit is big. Imagine a big circuit and you have many angles and many auxiliary at the input and output. It's not so clear if there is another one with different parameters which can do the same. And so we will answer to that. And so the question is KF. So let's take that big circuit. So it's I took a circuit, but it's very generic. We saw earlier that the triangular is basically the most generic form for anything we can do with space shifter and splitters. And I just put some sources and detectors at the end. So at that moment, all the rules we used for that is that circuit. Yes, so I just put all the sources and detectors on the bottom. So the free wires are on the top. So here the swap here introduced can be simplified in the triangle. Now I say we can have generic sources. So here I have generic sources on one node and one wire, here on two wires. But basically, we can see like if I have two wires, single mode, I can see that states on two modes, even though the states can be separated. I can see like that. So basically, we have a rule, and of course, it's rule with detectors that can basically compose the sources in parallel. Then what happens if you have a big source in front of a bin splitter of phase shifters? As we allow like any vector in the source, we just have to change the state inside the source, which is basically the semantic of the bin splitter. So we have rules like that, basically saying that if you have a state, a source, if you have a phase shifter, then you just add a phase on all the states in the source, and it is simplified. The same will be for the bin splitters. And so for now, I'm just showing like intuitive rules that the first thing that we can have now that we have introduced those kind of generic sources and detectors. And so we come up with that circuit, and you can see there are two identity wires. So for those who have understood the semantics, those wires, we don't need two identity wires. So for instance, it will be like kind of a product scalar between those. So if you have K1, K2 there and L1, L2, you don't need to have to, you basically can do a bijection from N2 to N to simplify. I won't go into details, but there is a rule maybe to say I can reduce one wire, I don't need two identity wires. So here we have rewritten our circuit to that form. And now I will try to show you that it is almost the unique form that we are trying to look for. So for now, we just take that example. So it can be generalized, of course, for n inputs and m outputs, but I will just take that circuit for all the presentation. And so the thing is, the proof that this part is unique is like, first we will show that the angles of the bin splitters and phase shifters inside the circuit that we couldn't basically just absorb in the Sources and Detectors, that we couldn't trivially absorb, those are unique. So basically all the theta and phi here are unique. And then we will show that the F and G, the pair is not unique. However, we will be able to find a unique representant of all the set of F and G that are working. So basically, we prove the LOP part is unique, and we'll find conditions on F and G to say it's not unique, but we have a unique representant, and we can rewrite to that representant. Okay. So let's do like the first part. So to do that, we do an induction. And so first we show the uniqueness of the base case. Base case will be, I have one input, one output. And so here, I won't go into the details, but it may be a useful technique for other proofs. How did I prove that? I took the inputs. So basically, I say, okay, let's take n input, n photons for n the input, n plus k photon and input output, and I will tend that n to infinity. So basically, I will look at the equivalence of the diagram of the left compared to the equivalent of the diagram of the right when I tend the number of photons to infinity. And I showed that necessarily, if you have a different theta and phi, then the equivalence in infinity will be different. As the semantics are the same, of course, it can't be the case, so the angles are unique. So basically, the base case is just a technical proof of saying I go to infinity, and the angles need to be the same. when we have the base case, we can do an induction. So of the minimum of input and outputs. For instance, let's take that example that we showed here. We want to prove that the angles of the log part, theta and phi, are the same on both sides. By induction, what we can do is like add the semantics are equal. In particular, if we add one source here, if we on the second wire, then it is still equal. Then we can apply the induction property, and that property say, oh, that diagonal, the theta 1, 1, theta 2, 1, etc., are equal. So we have equality on the first diagonal. But that kind of trick, like by finding like the good way to go under dimension which is lower than that, we can basically prove that all the parameters are equal. So there is something hidden, like it's not like the induction property is not directly or all the angles are the same. It's about the subunitary of the circuit, but in general, the idea is that. So okay, so we're happy. We are happy because the log part is unique. Then we need to find the uniqueness, the condition between f and g, and that's where the fun begins. So what did I do? I noted that kind of circuits, so general circuits, can be decomposed with in the basis of omega. So omega is between just you take your lob circuit D in the middle, and you fix. It's not a generic state, but just a single mode ket. So I1, I2, for instance, and G1, G2. So I don't know if you have any question, but the idea is to decompose that into a basis, which is simpler and easier to deal with. And that basis, that omega, basically are unique. What we will show is that if you want fg to have the same semantics as a f prime g prime, then you need the equality for the omega ij.
Just
yeah, sure.
Yeah, excuse me. So just a question here, because the omega ij is can be 0 or not? Because if g is just the identity, then if I1 is different from J1, it's 0, and in that case, the omega ij are not necessarily the same in the two for different pair f prime g prime, or does it make sense?
Yes, exactly. So it's always I should have precised earlier. I hidden some things. So you're perfectly right. In fact, I didn't precise it, but there is a condition on D, and the condition is like you have non-zero angles on the B splitters. For instance, earlier, if you have that kind of circuit, okay, if you have a 0 on theta 2, then you can remove again one identity wire. Like you can reduce the size basically of f and g.
Okay.
So when you have that kind of specific case of 0 angles, then you first reduce the maximum that you can, then you end up with a D which has non-zero angles, and then you have a non-zero omega.
Okay. Thank you.
So very good remark. And so, okay. So now, for now, there will be a lot of notation. So just be focused on. I mean, if you want to follow, just be focused on the ID. So here we want to find a unique pair of Fg, which is representing all the other pairs and so the only condition we need to satisfy is that. So basically, if you need a pair, if you want for them to be the same equivalent, you need that condition. And so we can just quickly look at the tilde F and tilde G. So the idea is G is basically a sum of everything, which is here copied. It's not an infinite sum, because like the set K here of index of summation is finite, because as the sources and detectors at the beginning is finite in lo-fi, then the decomposition of omega is also finite. So we don't have infinite sum. So it's okay to have that kind of sum. And here we can check that if you take G tilde and you put G1, G2, then necessarily L1 and L2 has to be equal. Then necessarily you have K1 and K2, which is equal to L1, L2, so G1, G2, and so you will cover that. So that's not the one I chose because we have two identity wires. But once you understand that, then you can just remove one wire by taking a bijection from N to N2 or the inverse. And so instead of having a sum of L1, L2 and copy L1, L2, I have just a sum of a pair. And instead of the copy, I just have the bijection. So maybe in the paper, if you see a bijection at some point in the normal form, it will be that reason. It just instead, so instead of having a lot of identity wires, I just prefer to reduce it to just one small wire. And so here we have unique Heurtel and Heurtel, but only with the hypothesis that the omega are very unique. And I also didn't specify how to write it. And so now I will explain very briefly how we prove the uniqueness of the small omega. And from my personal point of view, for now, it is, for me, maybe the most, maybe one of the most useful operators that I used in the proofs. So how to prove that they are unique. And so to do that, we could work maybe with the semantics directly on the states, but it's very hard. As you can see, the semantics of the B-splitters is hard. So even if omega, which is just single sources and detectors, seems not too hard graphically, the semantics is hard. And so to simplify my life, because it's good to simplify life sometimes, I used a bit of physics. So in particular, I use the creation operators, which is that kind of thing, like a dagger, which is basically created one photon. And as you can see, I did a typo. There is a nj plus one, so there is one photon more here. But okay. And a good property of that, it is like if you have a lob circuit like B-splitter phase shifters, and you have creation operators before, then after you will just have a linear, basically combination, linear relationship for the commutation about the dagger. Daj is like the coefficient of the matrix D, so in single photon semantics. That's the formula. Let's just show graphically what it means. So I will just informally represent the creation operator with a plus to say I just add one photon. So if I have that circuit, for instance, so just omega, then it is proportional because I don't want to precise like the square root of A1, but it is like the same as that circuit with a source I1 minus 1, and I add one photon, basically. Of course, A1 is greater than 1. And that, with the formula I show you, is like a sum. When you propagate the plus, you will have a plus on the first wire, on the second wire, on the third wire, and the fourth wire here. And it will add one photon somewhere on the first, second, third, and fourth wire. And so we know that. We know that if there is one photon, like it will be well, on one of the wire. But here, as it is creation operators, we can propagate one at a time, and we have only linear relationship between that. And so, which is cool, it is that thing would be useful for proving the uniqueness of omega. So that's why I introduced another basis, which is called delta. So I will introduce delta, which is informally, like graphically again, like that type of circuit. You have 0 photons as the sources. You have creation operators on the output wires, and you have detectors. Related to what Simon talked about, so it is important to have the circuit in mind, especially that we consider non-zero angles for the distribution. So just to have this picture in mind. What is cool with that? Why do we do that? Why do we use physics for introducing that operator? Is because we have what I call a threshold property, or at least a nice property, which is saying that if we don't have enough photons on the input or don't have enough photons on the output, then the value of delta is 0, which was not particularly the case for omega. So we can try to understand that. So for instance, if you put, let's start with the output. If you put, let's say, 2 photons on the first wire of the output, if you want to detect 2 photons on the first wire of the output, if S1 is greater than 2, strictly greater, and then you know it won't be possible. You know you will have necessarily more than S1 photon on the first output wire. So if you don't want to detect enough photon on the output, then it will be 0. Same for the input. If you want to inject just 1 photon, for instance, as you need to detect T1 and T2 photons here, then it also will be 0 if T1 and T2 are greater than 1 here. So it is a nice property of the delta. Another nice property is like there is a relationship between omega and delta. I remember earlier with the omega, I could just have a linear relationship and creating other delta. And so we can go from one basis to the other. And so thanks to the threshold property, we show that the delta are linear independent. So linear relations of delta are unique. And as there is a correspondence between the omega and delta, then we conclude about the uniqueness of the omega. Just mentioning, so the omega are unique. Then the pair, the tilde F and tilde G I presented to you are.
It's the closest that I have right now. I don't know if it'll work. Please mute your microphone. Yeah.
So,
Nicolas, because you're host, I think you might have to mute Neha.
That's fine.
You good?
Yeah, I think it's good. No worries, Neha.
So yes, so the omega are unique. So we know that the tilde F and tilde G are unique, but then I just need to explain a bit how to write to it. So just briefly, we can introduce, for instance, a rule, so like that, so saying that I will transform G into that kind of form. I didn't introduce the notation here because maybe the notation in the paper will change a bit, and it's a lot of energy in the mind to understand the notation. So let's just say we can introduce a rule to do that. We also have rules that can trivially adding terms which are 0, and we can basically converge with that. However, those rules may be a bit complicated. In fact, it was a lemma. Actually, it was a lemma. So in practice, I will just go through quickly the rules before concluding. So here are the rules which are mostly about just slop, except from the 0, 1. So practically rules that you may be familiar with. And the second, so it will be most of the times rules that are quite intuitive and that we used earlier. So for instance, if you have two sources, you can compose them. Same for the detectors. If you have sources and phase, you absorb. Same with the beam splitters and detectors. So basically, the only rule that you didn't see was S0D. So basically, when you have a source and you want to detect zero, it will project just under the term with the zero photon on the last. Reversibly, if you want to understand the rules from right to left, it just means that if you have a source there, you can create a state bigger and just if F0 is the state with zero. You can add more terms, which are trivially zero, but and maybe the last one, so sorry I didn't introduce again the notation, but the last one is just saying if you have a function acting on the last two wires on the source, then you can just propagate the function on the last two wires of the detectors. It's basically, imagine you have a box H, a function that you can propagate in the two wires. So I would say pretty, I mean, aside from the notation, which is not easy to understand, but aside from that, the rules seem pretty standard. And so now we come to the conclusion. So first, there was a simpler equational theory for LOP, which may be used to other things, where we removed some phases in the equation, and we also had explicit and reversible rules. More importantly, the main result of the work is to have unique forms for lo-fi circuits. So basically, linear optical circuit with ancillary sources and detectors, we have now the uniqueness of that, the form and the proof of uniqueness. And also, the proof introduced, so I introduced them briefly, but the omega basis and the delta basis, which have both their own pros and cons. So the pro of the omega is like it's quite intuitive. The pro of the delta is like it's useful to prove things. And so obviously, one of something to look at for the outlook is, can we use those operators to other things, like other just to be tools for a proof? Can we use the delta basis, for instance, as it has a threshold property to synthesize circuit, to find circuit? Another thing is like to look at maybe states and effects with infinite support. The reasons of why we didn't hit in this work was just technical reason. The proof didn't apply, but it doesn't mean that that there is no unique circuit, or maybe there is. And the last will be maybe, of course, so I didn't look at it recently, sadly, but to link with other languages. So that can be the techniques, but also, of course, that can be the graphical. So there are a lot of works about that, and we're very, very happy to share or to talk and to discuss that. On the matter, I'm going to QPL, so if you are also going to QPL and if you want to talk more, I would be very happy to do that. And thank you for your attention, and thank you.
Thank you, Nicolas. Everyone can either clap or give the clap emojis, whatever you like to do to thank him. And I'd now like to open the floor to any questions.
Yes, Paul?
Thanks for the talk. Can you go back to your axioms? The last slide, I think.
Sorry, can you repeat? I think it was...
Can you hear me?
Yes, perfect.
Can you go back to your axioms on the previous slide?
Yes.
So this last axiom H2 is kind of strange because you're not compact close, but this is like not a convex like axiom, right? You're like matching on something with a hole in the middle. Is it?
Yeah, so yes, indeed, like there can be anything on the middle. As maybe that can help you. I'm not sure to understand the problem, but maybe I didn't precise it. But H, I mean, as it is finite state, H is just can be just a linear operators with finite support. So
Okay, I just want to make sure.
Yeah.
It's kind of unusual. I don't think there's not any other graphical languages with a rule with a hole in the middle, other than this one that I know of.
Yeah, but it's because like the generators are quite big. So yes, you can see at the hole of the middle, or you can just see it's a source and detectors. But indeed, it is a very powerful rule and a big one.
So just it looks like a trace, right? Because the H is going from
Yes,
right to
exactly.
left. So it's a kind of trace, I think.
Yeah, exactly. I didn't formalize it that much, but yes, would be a kind of thing.
Do you know, does this actually have a trace, like a proper trace, or is this is like a separate kind of thing?
So I don't know for that.
I know that unitaries have a trace, but this is not the same. This is an extension.
Yes, it's not unitary, so yes, and also like it didn't precise it, but you can basically it works for any age, so you can choose the age. So.
I have another question. Maybe this is naive, but is this expressive enough to like get the like H star algebra structure of the number basis? Like, is it you derive like the qualification map for the thing that copies number basis elements, for example? Of course, that does not have finite support.
I don't hear you well, Cole.
Is this better?
Slightly.
Yeah, can you is this expressive enough to capture the like H star algebra structure of the number basis, like where you copy, for example, the diagonal map which copies number basis elements? Does that live in this semantics?
So the quick answer is I don't know. I don't know. Maybe Simon has more insight about it, but
Okay, thanks.
By the way, if you have a paper talking about that, I would be glad to follow up.
It's just because this paper by this Fock up ZX calculus.
Okay.
They do this stuff using non-standard analysis, and they have this new spider for the Fock basis. But I was wondering if you could, if it's just an H star algebra, if you don't ask for the unit, then it actually lives inside of Hilbert spaces. So I was wondering if could like if it lived in here, if you could kind of reframe the generators to be more ZX flavored. But I'm not sure if it actually is.
Yes, Simon.
Yeah, thanks for the talk. I was wondering if you can turn your equational theory into a rewriting system, something like this.
So
or do you have a strategy to?
So yes, so the sorry. So the axioms, so here, not really, but you can have a lemma. I mean, you can have oriented equations with, or at least a strategy to rewrite to the normal form. So it was in the appendix on the archive paper, but there are some lemmas saying that, oh, do that, do that, do that, do that, and so I don't know if it's confluent. I mean, but at least there is a strategy, the deterministic strategy,
Okay, thank you.
which is also kind of natural. Like we did like together the strategy of just absorbing everything and reducing the wires, and then there is at this point a strategy to change FHG to the normal form of the normal form. So the first one is quite intuitive, and the second one is basically changing FHG in the correct way.
Okay. And so maybe just a technical question, but I was just thinking that, so if your initial diagram does not have this this identity on the bottom, so you can add it with a with the zero rule, right?
Exactly. That's exactly. Oh, sorry. It was. I went the wrong way. So yes, exactly. There is the zero rule, which is adding identity wire for free, and which is just saying you sum, but with one term in the sum, but it's still you represent it as a sum. So.
But then you are not losing the uniqueness of omega something because of this zero, or
No,
I should look at the paper.
So no, that's a good one. So the thing is, when you have just no identity wire and 1 0, it would be like that. Then the circuit is already just 1 omega, just one. I mean, not really, but depends on what you have in the sources. But it also can be a sum of omega. So as soon as everything can be a sum of omega, then you either there is a identity wire at the start or not, it's okay. And if there is no, you can add one and then use the rule to still transfer all the coefficient of G into F.
Okay. Okay. Okay.
And so indeed in the procedure of do that for the rewriting, there is a line to say if there is no identity wire, add one, and then continue as planned.
Okay.